Hello? Get started, huh? 1 minute early the first day ought to be okay. Okay, welcome. I don't know whether I should say welcome or good morning or good afternoon. I guess good lunch or whatever. But this is a class EECS 240. It talks about analog integrated circuits. And well, it's the year 2004, I guess, whatever I write here. Huh? So let's talk first a little bit about the administrative issues, and then we'll talk about the content of this class. So first of all course material is on the web, including this presentation that I'm using today. It's almost the same as last year, so if the updated version is not there, then you may want to consider to print out just what was there from last year. But often they come up sort of Monday, Tuesday, or sort of the day or the one day before the lecture, the day of the lecture. And it probably, of course, is convenient if you manage to print them out, so you can mark them up. So the scope, of course, we will talk about. One of the topics that always gives rise to questions is that of a textbook. And there is no textbook for this course, and the reason is simply that no textbook is written that actually covers what I want to cover. What I want to cover is not a long laundry list of analog circuit tricks and devices, and you know, we had another amplifier configuration and so on. You'll figure that out. It will be different next year, and it certainly will change a whole lot over your lifetime. What I want to teach in 240 is to take specifications for analog circuits, or figure out what reasonable specifications would be, and then go through the process of finding a somehow optimal implementation of a circuit that realizes these specifications. Unfortunately, most books, they don't cover that. That is not to say that books are not helpful. Quite to the contrary, and so instead of requiring you a text that sort of would imply that whatever is in that text is what I'm teaching here, I just said that thing doesn't exist. I've made a list of texts that I sort of recommend, and if you ever come to my office or office hours, then you will see I have a quite extensive library of books, and I sure use them. And if you are serious about analog circuit design, then you will pretty soon also end up with a fairly extensive library, plus a few things that maybe you haven't gotten from these books, maybe the one or the other even from this course. So I have, if you can zoom in a little bit here, please. Just all of this is on the web, so and here at least. Oh, okay. There's no focus. Huh? Okay, more or less. Well, but now make it big again. Okay, so among the recommended texts is I oscillate between texts, but now it's again Gray and Meyer 4th edition, or the most recent edition. That's a good text that covers a lot of, gives a lot of mileage. It will complement a lot of the material that I go over here. It has good exercises. If you do those, you want to know answers, I have those answers, and I'll be happy to help you out with them. So that's a good text to have. Another good text that is quite unique, and it is still out of focus. Okay, good. Another good text is the one by Hastings, The Art of Analog Layout. Now, I do not particularly like the title. If this was an area of artists, I wouldn't be here. I would be admiring, but I wouldn't be here. But anyways, analog layout is not an art. It's actually also something that, sort of an engineering discipline, right? And of course, it's important because circuits that are well designed and not laid out correctly, they don't work, right? So there is little material on that. Most of it is sort of hidden in companies. They have gurus, right? They've been there for 20 years and they know it by now. Well, this text has some good insight into layout considerations. And then I have a list of of references. The first couple are analog circuit books, circuit text, Razavi, and so on. Actually, Cividis, that is a perspective of integrated circuit devices from a circuit designer's point of view, as opposed to physicist's point of view. And well, you can read through this list yourselves, and you may find one or the other text could be beneficial. And you can also check them out in the library. They are on reserve there, so you may possibly make a decision what you want to buy. Then another topic that also is covered on this overview sheet here is grading. In this course we have homeworks. The homework shouldn't be particularly hard, but they should provide feedback that you certainly went over everything that we talk about in class, and that you also get feedback whether you actually understood it or not. If you have difficulty, then please come see me at the end of class, or ask a question during class. That's in particular good, because chances are that whatever question you have, your neighbor actually has the same one. So, and then of course there is office hours, and there you're also most welcome to ask your questions. So, so homeworks, most people will get that correct, and so that will give you sort of a fairly solid basis for your course grade. The project is also something that is sort of like a very large homework, although I tend to make it somewhat smaller than in past years, and that also is something that where most people get a fairly good score. And then there are 2 exams, a midterm and a final. So there's a sort of half between exams and homeworks and project. That makes up the grade. Are there questions about that? Okay, so so office hours, well, yeah, here they are just listed. My office is in Corey Hall 519, and Tuesday, so after today's lecture, there is 1 hour of office hours just immediately following this lecture. And then on Thursday, we have another office hour from 4 to 5. You're, of course, welcome also to send me email. Like everybody, I'm getting a little bit too much of that, and so if I do not answer or do not answer right away, it's not because your email is not the most important, but it's just because several unimportant ones somehow messed up my inbox. Okay, so what is this course about? Well, first, there is this problem of analog circuits, and then there are, of course, also digital circuits. So why the heck should we even deal with analog circuits, especially considering what's happening in digital circuits, right? They just get better. You can't help it. And there are many ways to determine how they get better. If you have a computer and who doesn't, then you sure know that digital circuits get better. Another way to actually capture that is the cost per function. Let's say the cost per 32-bit multiply in terms of silicon area, for example, or the cost for a more complex for a memory or so. For digital circuits, they decrease consistently and significantly. They decrease about 30% every year. Right? So that's commensurate with every 3 years we get a new computer that is 2 or 3 times faster or more powerful, and it costs the same or less. Right? So 30% per year, that actually translates into 30x over 10 years. That's the reason why today, with your laptop, you have more compute power available than 10 years ago with a supercomputer that cost $1 million or more. Right? Extremely, extremely mind-boggling changes, right? And that's also maybe not absolutely unique, but quite unique for our field. And we need to be aware of that all the time. When we design something, we got to not only say what it is, we have to also say when it is. Because if we design something today, but for 2 years back, well, characteristics may not be so. For specifications that were appropriate 2 years ago, that thing will not be that attractive today, right? It should be 60% cheaper. Okay, so how does this digital stuff compare to analog circuit? Well, first of all, the reason, of course, why digital circuits get cheaper and better is the technologies get better, right? Especially feature size, and we'll talk a bit about that later on. We'll see that analog circuits, they benefit from small features. If I have a 0.25 micron technology for my analog circuit, I probably can do a better job than in a 1 micron process. Okay? And for 0.12 micron, probably is true also, although then it gets a little bit more complicated. But nevertheless, even though analog circuit designers benefit from technology scaling, the benefit is sort of a mixed bag. It's a mixed blessing. First of all, the cost per function of analog circuits isn't really decreasing rapidly. It's probably decreasing a little bit. For some things, decreasing a little bit at least. For others, it's not decreasing at all. So the cost per function for analog circuits, give or take, is about constant. And then we have a second thing, and that is technology scaling is, again, is a mixed blessing. Deep short channel devices have very low supply voltages, like 1 volt or so, or 1.5 volts. That's a problem for analog circuits. And that actually may make them perform suboptimally, and we'll see why. It may also make it just about plain impossible to build an analog circuit. For example, if you want to build an amplifier that has a gain of 1 million in a 5-volt process, well, you have plenty of opportunities on how to do that. In a 1-volt process, I don't think it's impossible, but it's very, very hard. Right? But sometimes you need a gain of 1 million, right? So analog circuits sort of, in this very deep submicron technology, they're kind of, some people question, well, at some point, maybe we have to abandon that, and we have to go to a 2-chip solution where we have 1 chip for the analog function, and another chip for the digital functions, or something like that. Anyways, all of what this means is that we will see a transition to DSP. If you can do something with digital circuits, you probably not only have to, but you also should, because you get benefits that you just can't get from analog circuits. So, what does this mean for analog circuits? Well, before you run away, let me quickly answer that question. Well, obviously, the reason we build analog circuits is that we need interfaces to the real world, right? To the physical world. Digital circuits cannot possibly take even the simple stuff like what I'm talking here and sort of convert that. And they need first an analog circuit that takes the output from a microphone, amplifies it, filters it, performs an A to D conversion, and then the digital circuit gets into action. So analog circuits increasingly is an interface technology. It interfaces between the physical world and digital circuits. And so the options is exactly where you want to put this boundary. Do you want to do more analog processing first and sort of a little bit less digital, or do you want to do more digital and less analog ahead of time, and so on? But one thing that is very good about analog circuits, at least if you're an analog circuit designer, is that in many applications, actually increasingly, analog circuits are in the critical path. In other words, you can do the next great thing, the next great product that you'll make millions with, if you can do the analog circuits. The digital circuits are kind of a given. You use the next process and the most wonderful synthesis tool and a few other things and a few and then you can do the digital part. The question is, can you do the analog interfaces? A good example is software radios. Right? People, they want to put the A to D converters right at the antenna, or for example a cell phone, because then when you travel to a different country, that uses a different standard. Well, you just load in a different software, and your cell phone is converted to that standard. Well, there are probably some challenges on the digital side also for doing that. But the main challenge is on the analog side. Today, it's just plain unfeasible to build the analog circuits that you would need in such a software radio. Okay, so let's go over a couple of examples of where analog circuits are used. Well, this here, if you can use more zoom, and then I'll slide my slide around. Thank you. Just more. I will slide around. Okay, so that's from my own research, actually a few years old by now. But it sort of exemplifies how and why we need analog circuits, and then also how and why we want digital circuits. This is an accelerometer. In fact, it happens to be a 3-axis accelerometer. Here in the middle of the device, we've built physical sensors, accelerometers. They are pieces of polysilicon that move around. If I move this around, right, and this motion of these polysilicon pieces is then measured. Well, how do we measure that? Well, the first step is that whenever two things move with respect to another, they kind of have capacitance between themselves, between one another, right? And if they move, so the capacitance gets bigger and smaller. So that's the basic idea. But the minute we have that, well, the next thing, of course, is an analog circuit. Now, why is it interesting and challenging to build an analog circuit for such an application? Well, these things, they move around pretty much nothing at all. In fact, the motion of these plates is far smaller than an angstrom to accelerations that we want to detect. In other words, what's the distance between two atoms in the silicon crystal? 2.5 angstroms, right? I mean, this measures something that's 1,000 times smaller. In fact, it measures something that is, I have a physics book, and I don't know what it means, but I looked up a number, and it says classical radius of the electron. And then it's a mind-boggling small. I've forgotten what it is, but this thing, this analog circuit, manages to detect motion that is on the order of a few classical radii of an electron, right? Extremely small motion. Okay? And of course, the trick is to build very sensitive analog circuits that take capacitance, convert that into voltage without introducing errors. An important consideration here is going to be noise, and we're going to talk a lot about noise, because noise, turns out, has a lot to do not only with the performance of a circuit, but also with how much power, for example, it dissipates, how big it has to be, and all sorts of other interesting things. So a typical analog circuit application looks something like this. There's some kind of a sensor here. This is MEMS stuff. Then there is a very sensitive analog circuit. Then there is an A to D converter. And now the rest is digital, right? And the digital port we haven't even bothered building here. There's pads, and then it goes into an FPGA, and the FPGA realizes the digital stuff. Right? There are, of course, plenty of other examples. I don't want to go into too many of them. An RF receiver would be an obvious another obvious other one. Right? You have an antenna. Signal comes in. It's very small, very high frequency. You first bring it down into a frequency band where sort of processing is possible. Make it a little bit bigger. You convert it to digital, and then the rest is for a DSP. And something similar goes on in the transmitter. You can look at that slide. It's posted on the web. So, if that's the kind of application we want to sort of sharpen our analog circuit design skills with, what kind of skills do we have to tackle? Well, so the key number one and central topic of this course is amplifiers. It turns out that they're really kind of the gates of analog circuits. So what is an AND gate, give or take, for a digital designer, is an amplifier for an analog circuit designer. If you want to build an A to D converter, probably critical element you will get pretty soon to designing to is an amplifier. Right? If you build a radio, need amplifiers, and so on. Hard disk drive, name it, amplifiers are critical. The other reason why we spend so much time on amplifiers in this course is that they kind of force us to look at pretty much most of the analog design issues that then are also relevant for other analog circuit stuff. Right? There are a few other things than amplifiers in this world. Right? Device characteristics, we need to know devices, and we need to know specific things about devices, and we'll talk about that more today. They talk about electronic noise, or they depend a lot on electronic noise. So amplifiers are a good vehicle, a good context in which to talk about electronic noise, not to become physicists. Right? We still want to be analog circuit designer. Frequency response, step response, feedback, stability, those are all fundamental techniques of analog circuit design, and of course they are linked very strongly to amplifiers. The focus of this class, and I said that already earlier on, is design. What we will do over and over is we will find ways how we take the specifications for an analog circuit, so for example an amplifier, and then we somehow transform those into a design, into an arrangement of transistors, and ultimately into a layout, or at least a list of device sizes and so on. Okay. So amplifiers, they are sort of the core of the course, but then there is a bunch of stuff that goes around them, and we will talk about that also. I've already mentioned we will talk about devices, and we'll start with that topic actually today. And then there is lots of sort of what I call here support functions. For example, we need to have biasing networks. Amplifiers definitely will need them. I will spend a bit of time on doing those, and they can be quite a bit of work, so being organized about them helps. References, right? We would like our analog circuits to operate from varying supply voltage and over a wide temperature range. Well, for that we need references. If you have taken EECS 140, then you already probably studied quite a bit of them. And so we'll add here a little bit more. For example, what happens if you get to build a reference in a CMOS process and there just isn't a bi-CMOS option available, right? Okay. And then another circuit that is extremely important for building CMOS circuit. That's actually the reason why CMOS circuits are so successful, and why ultimately they, in most areas, replaced bipolar transistors. And that's the MOS sample and hold. The fact that you can take a voltage, you can sample it onto a capacitor, you can open some kind of a switch that we have to build out of transistors, and we'll talk about that. And then you can leave it there, and you can use it later. It's as simple as that. But that's the thing that makes CMOS technology so versatile and so powerful. If we didn't have that, probably CMOS for analog would be in huge troubles. Since we have that, it has lots of advantages. Comparators is another sort of obvious thing. Of course, there are several courses on analog circuits and here at Berkeley, and I mentioned just two of them here. One of them is 240 and 247, and so kind of how do they differ? Well, 240 is transistor level building blocks. It looks at device and especially circuit fundamentals. It has, relatively speaking, little abstraction. Right? We really deal with transistors, and very often with parts of transistors or aspects of transistors. And so the world, if we use the computer, our world is SPICE. Okay? 247 is a mixed signal course focusing on the analog part of the mixed. It looks at macro models, behavioral simulation, large systems. It looks at things like A to D converters, filters, and it looks at them with a relatively high level of abstraction. So rarely in that course will we look at the transistors, but instead we will look at the entire function, and we will sort of break it down to, well, we need amplifiers, and what are the specs for this amplifier, and somebody who has taken 240 can then design them. Right? Simulation in that course uses MATLAB, Simulink, again, relatively, for my taste, high level, right? Depending on the perspective. So these courses are very complementary. For example, A to D converters, well, we sure talk about the fundamentals and basic elements that we need to ultimately implement an A to D converter. For example, we'll talk about the reference. We'll talk about layout issues. We'll talk about power supply issues. We'll talk about, did I say amplifiers already? Certainly. We talk about those. Reference networks and so on. We talk about all of that stuff, the sample and hold in 240, but we will not talk about the entire architecture, the entire beast of an A to D converter. That's a 247 topic. Right. Okay, so that's the introduction. That should give you an idea of what the heck this course is about. Do we have comments, questions, suggestions at this point? All right, so then in the beginning there was the technology, right? So let's start there. And before I just totally bore you and you all leave this room, I guess I need to address the question: why bother and look at devices yet once again? If you've gotten to this point, without doubt, you've taken your share of courses that either are focusing on device physics or at least have a significant part of device physics in them. And probably for about half of you, or maybe even more, you've about had it. And you want to do something with these devices now. So why in the world, in a circuits course, I start with that same old hat? Well, we'll talk about various things when we talk about devices, but there are two key issues that are not usually addressed in device courses, and therefore need to be addressed in device circuit parts of circuits courses. Right? So as we go over that, keep these two issues in mind. That's the thing that ultimately you ought to understand. Right? So before you completely get lost, turn back to this slide and look what it says and see whether you've learned something on those issues. So the first thing is the perspective. Well, see, if we talk about devices, we can look at them from many different angles. One of them is physics, of course, right? We can talk about quantum mechanics even and so on. Well, that's not for the circuits course, right? Another angle to look at devices is device dimensions. Well, if you're layout engineers, you don't care about what this device does. You don't care about the current. You don't care about the noise. You don't care about any of those things. You want to know how big the thing is so that you can push the right button on your CAD tool and plop it down. Right? And even if you use design equations that are very popular in Graham-Meyer or in 140 or so, the first thing you got to put in is mu Ciox W on L, right? So W on L takes center stage. Well, I can tell you one thing. If you want to be a good circuit designer, put that a little bit on the side. W and L and mu and Ciox are rarely very interesting when you're designing a circuit. Why? Well, because when we design a circuit, you want to achieve something. We want to achieve a function. And well, what is that function? We want to do something fast. We want to have a certain amount of gain. We want to have low noise, right? And also we want to do that with a lot of efficiency. For example, we want to pay little for doing all of that. ID, heck, I mean, if I could, I would make ID always 0, right? It just drains current from the battery, right? So So my perspective as a circuit designer is not, how big is this device? My perspective is, what can this device do for me? How fast can it go, and how much current do I have to stick into, and how big ultimately do I have to make it for that then? But the dimension is sort of almost an afterthought. Ultimately we'll be getting there, but first we have to concentrate on just what the heck we want from this device. And so we will roll up device physics, if you want, from a little bit different angle, from the angle of a circuit designer. What can these devices do when we make them bigger or smaller or so, right? And then we will invert it, and we will go from specification to ultimately dimensions. But the dimensions, once we're there, they're pretty uninteresting, just numbers, right? So that's the first point, right? When we talk about devices in 240, we mean something that is probably a little bit different than a guy in a device class who models, you know, the wrinkles and the nth deviation from some physical model of a device. The second topic that we are going to address is what I sort of sweep up in short channel characteristics. That's also something that you, without doubt, you've come across, right? In pretty much every device course, and certainly in every circuit course, they teach you first this wonderful model that usually is called square model, right? ID equals 1/2 mu C ox WNL VGS minus VTH square. So that's square law model, right? Wonderful. Then you use that, and you somehow, some foggy way usually, relate them to what you actually want to do, and you come up with a circuit. Plop that circuit into SPICE, simulate it, and the first few tries, SPICE usually says that there is a floating node or so. Once you get over that, then SPICE gives you characteristics. You've got nothing to do with what you've designed for, right? I mean, if they're just a little bit off, 20%, and you are lucky, usually they're just plain off. It's just something different, right? If you had wanted, you couldn't have that designed that crummy thing. And the reason, of course, or one of the reasons, if you haven't made mistakes, is this square law model is woefully inadequate if the channel length of the transistor is something less than a micron. And heck, I mean, when do we get the opportunity to use more than a micron, right? And actually, even if you use your 0.25 micron technology and make a transistor that is 5 micron long, then it still won't behave according to this square law model, because it was not only the channel length that was shrunk, but also the gate oxide that was shrunk. And that makes it the transistors just plain. They don't behave like the square law model. They behave like something that is a lot more complicated. And if you go and look at manual for a circuit designer, then you find something like BC model or so, and you find that the square law model has been replaced by 20 pages full of equations, right? Now, the good part of these 20 pages full of equations is that pretty accurate, and most of the time they actually say pretty much what would be happening with that circuit if we actually had built it, right? The trouble is, of course, with 20 pages full of equations, nobody can do design, right? So that's the second important point why we have to got to look at equations. If we are serious about this design and don't just want to make it part of the title of our textbook or something like that, if we actually want to do this design for analog circuits, we have to find something better than the square law model, and we also have to find something better than the 20 pages, or now it's probably 100 pages worth of equations that circuit designers deal with. Right? Neither is going to cut it for design. And so that should be plenty of motivation. Why? Well, once again, hopefully for the last time, but I promise it won't be the last time. After this course, we will talk again about devices, but here we'll talk about them too. Okay, so now in order not to sort of get too deep into all these challenges and so on, we'll start a little bit easy. We'll start first with the CMOS cross-section. I find that extremely helpful to just know what the heck actually, what is all the stuff is there. Right? SPICE is always very nice. It abstracts. Before I called the SPICE a relatively low-level simulator, but it still abstracts a lot of stuff away, right? And so the CMOS cross-section very often is a good thing to think about. Well, what is it that we may have also there in our circuit that SPICE doesn't even think about, know about, and consequently could make a difference between what SPICE thinks the circuit's going to do and what reality is. And you won't be surprised if I say that most of the time the reality, unfortunately, is not quite as good as what SPICE says. So SPICE is a good check, but it's not an insurance yet, or no certainty, right? So after this cross-section stuff, we go and look at passive devices. They're a little bit easier to deal with than transistors, and that we keep for next time. Actually, it will take us a couple of lectures to look at MOS transistors. So first, the CMOS process. Well, there are plenty of CMOS technologies, of course, that we could be using here, and we could also switch between different ones. So for 240, we pretty much have settled on a 0.35 micron technology. I specified here the way usually these technologies are specified with these acronyms. 2P4M, that stands for 2 levels of polysilicon. We'll see later why 2 is better than 1. And 4M stands for 4 levels of metal. Of course, if you use a really modern technology, then this is not 0.35, but 0.09 micron, right? And the 2P maybe is then a 1P. They still give you a level of poly for the gate, but the other one's gone. And the 4M's mushroomed into an 8M or something atrocious like that. I have more. You have an entire... You have a kilogram of metal on your chip, right? So the minimum channel length in this technology is 0.35 micron. Again, that's not at all state of the art, and I will say something about that. Why I teach you such outdated stuff on the next slide. I've mentioned that already. The supply voltage is today relatively generous, 3.3 volts. Again, there are other choices. We could, of course, use a shorter channel length transistor that then has a 1 volt supply. We could work with bipolar, silicon germanium, HBT, SOI technologies, and so on. They're all important. Maybe one or the other one is actually going to replace what we are this standard bulk CMOS that we're talking about today. Who knows? I hope I can teach you design. Then you can take that design stuff, the information how to do design, and you apply it to another technology. Because granted, over the 30 years of sort of your active life, 30, 40 years of your active life as engineers, things are going to change a lot. But you're still going to do design, maybe with a different technology. So why 0.35 micron? Well, there are a number of reasons. One of them is just it's getting very difficult to get good circuits technologies, good SPICE models for circuit technology. They're always proprietary, and so I can't stick them on the web, and I have to make you sign 20 pages of non-disclosure with your own blood, right, and so on. Well, the 0.35 micron model that I have on the website, and on the website it's sort of free for all. You can get it. So that's sort of one practical thing. The other thing that is even more important, and you will appreciate that when you do homeworks, is that as we scale down device channel lengths, the technology side, we invariably also the supply voltage goes down. And you know, if we want to put together a little example to try something out, if you have sort of 3 volts available, it's maybe a tad bit painful, but you can do it, right? If you have to shoehorn everything into 1 volt, you're spending a week getting it into 1 volt, and then half a day to actually look at the effect that you wanted to simulate, or investigate. So having a little higher supply voltage makes it Makes it a lot easier. And then, of course, there is always, even in this 0.35 micron technology, nobody forbids us to push a button in SPICE and say, heck, now we try it with a supply voltage of only 1 volt. So we kind of have all the opportunities. But granted, once you're out of this class and you really get serious about analog circuits, you're going to be somewhere here and not here. Okay? Right. So I said that we wanted to look at cross-section. So here is a very simple, not to scale and so on, cross-section of a CMOS process. So first here at the bottom, this green stuff is the substrate. The substrate could be N-type or could be P-type. Today, most of the time, it's P-type. So that means that you immediately can make an NMOS transistor here. And the NMOS transistor then uses N plus diffusion in the P plus diffusion substrate, or in the P plus substrate. Right? Then invariably we get diodes here, right? And you got to tell SPICE that these diodes are there, and you got to tell obviously SPICE that how big these diodes are, because if they're not there, you may forward bias one of these diodes. SPICE isn't going to tell you about something that is not in the netlist, right? They are also capacitors, and most of the time, you know, we really didn't need them. But they're slowing things down, so a surefire way to come up with, you know, this next revolutionary A to D converter that goes at 1 gigahertz, and that is going to make you famous and give you a PhD, is to ignore all these junction parasitics, and it's going to go a lot faster, at least in SPICE. When you're fabbing, of course, it's a little different story, and so you may have to delay your PhD a little bit on that. So it's good to sort of look at that. Another thing is that the substrate also, heck, I mean, it's a node, right? If we pull it way up, we're going to forward bias these diodes. If we pull it way down, well, then we increase the junction capacitance. And if it's unknown, then this is just a path to inject signals into the source and the drain of our transistors, where they probably add in a not very constructive way to the signals that we actually want to process. So we want to keep this, we want to know what the potential is of this substrate. We want to nail it, and how do we do that? Well, we make a contact to it. Now, to make a contact, we don't want a diode, so we actually use a P plus diffusion. Again, SPICE couldn't care less. Leave it away. SPICE, everything works out honky-dory. If you forget it, your IC will not work honky-dory. So we can see this stuff from a cross-section right away. It's kind of trivial, right, obvious. So if we want to make a PMOS device, then we need an N-roll that is somehow put into the substrate. There are lots of ways to do that, right? Again, for that you can take another course. And then we do the same. We do the same thing. Now here it's even getting more interesting to look at the cross section, because if you sort of remember 140 SPICE, right? How many terminals does a transistor have in SPICE? Source, gate, drain, bulk, right? 4. How many terminals does this transistor have? Source, gate, drain, bulk, substrate. A terminal is missing in SPICE, huh? Realize? Well, why is that? Well, because SPICE says, I mean, come on, I mean, why bother? We have 20 pages worth of equations to model what's going on here. Why bother to also stick in this thing, right? So this diode isn't present. Well, it sure is present once you fab the circuit, and it sure has an opportunity to mess things up. So sometimes I draw this cross-section, look at my diode, figure out how big is it, and then stick it as an extra element into SPICE, just to be sure. Right? I will talk sometimes about this diode, this course. Okay, so a little bit about dimensions. First of all, the wafer, 700 micron thick or so. That's primarily determined by mechanical stability. And in fact, wafer thickness is going up simply because the wafer diameter has been going up. But now if you have something 12-inch, right, if you make it 300 micron, it's sort of like a piece of paper, but a little bit brittle and it's going to break. So they can be fairly thick. Really used for the circuits is only the top micron or so. So there is the well. The well actually goes relatively deep, maybe a micron or so. Again, as we progress to shorter channel length devices, that dimension also goes down. Used to be 5 micron. The junctions themselves, they are fairly shallow, a couple of tenths of a micron or so. And their depth has to be in some relation with the length of the device. So the length of the device is the distance between the source and the drain, and the minimum in our process for 240 is 0.35 micron. Right? Also, if you come from like a 140 background, then you know that there are really different kinds of lengths. There is a physical length that is really the physical distance between the two, and this is a PMOS transistor, so the two P plus regions here. Right? And then there is also a drawn length you have on the mask that is a little bit longer, right? And then there is this LD business that accounts for the difference of them. It's one of the things that we are going to throw out the window in 240. Why? Well, because it just adds an extra parameter to our model. But once you go to deep submicron technology, it doesn't add any extra accuracy to our model. So we do something that gives us the information we want without fussing with LD. So we have one device length, and we know that physically, well, then in the transistor, some more complicated stuff can be happening. Okay? So we just have the drawn. The one that goes, what the layout guy knows to make his mask from, that's our channel length. No other ones. Okay, well. Okay, so now with this IC technology, we can make actually quite a few devices. We can have active devices. That would be the N-channel transistor and the P-channel transistors. We kind of can make diodes. Actually, we have lots of diodes here. They're not, unfortunately, not nearly as useful as one might think, because if you have a diode in between here, well, does the current flowing between these, the minority carrier current, flowing between these two junctions, or in this junction, does it want to go into this junction, or does it want to go into the substrate? What do you think? What do you think? Heck, what's bigger? The substrate is all around it, and then there is this small junction somewhere over there, right? So if you forward bias this diode, most of the current actually ends up in the substrate, like 90% or so. So these diodes are conditionally useful, right? If we want a diode to the substrate, sure, we can have it. Now, actually, if we look at this stuff here, then we have here P, N, P. Heck, we've got a bipolar transistor also, right? It's good to look at cross-section sometimes. This wasn't a bi-CMOS option that we paid for. We just got this bipolar transistor here. Should we care? Why? Okay. So, well, that's a good perspective for an analog circuit. Always think about the trouble first, right? Right? Yeah, you're absolutely right. This thing is going to latch up on us, right? Of course. So we're going to use an epi substrate or whatnot, or put a lot of these contacts all over, or probably both. Right? But then there is one other thing about analog circuit designers. That's why they thrive. So we know about all these troubles, right? It's going to go wrong. And because we always check that it's not going to go wrong, in the end our circuits work, right? But then we also, the minute we've checked into the trouble situation, we say, well, gee, can't we use this for something neat? What could we use this bipolar transistor for? Well, references. If you want to make a reference, you pretty much need a bipolar transistor, right? There is no band gap reference with, I don't know, MOSFETs. You need a bipolar. Well, we're going to use this bipolar. It's not ideal. It's not a very good bipolar, actually. But if you want to make a decent reference in CMOS, this is by a long shot the best one you can do. Much, yeah. And of course, it avoids having to add the BiCMOS option that may not be available. And if it is, it adds a lot of money for one transistor on your entire die, right? Yes. P, N, P. Right. Now, of course, well, we could also say P, N, P, right? And we probably would rearrange these so that this one would come somewhere in the middle. So we have a vertical. This is the vertical bipolar, and there is a lateral bipolar. They both are kind of crutches. This one, obviously, problem is that one terminal is always the substrate. Well, the substrate's equal to VSS, right? And so turns out in a reference, it's not good, but we can live with it. Here is the lateral PNP transistor. Again, we would rearrange that to get P and P, right? And this one has the disadvantage that as we inject carriers into the base, which is now this humongous top, right? Then like probably 99% of all the current ends up in the substrate. So it's funny. I actually did that probably about 20 years ago to just get an engineer's degree, a diploma. I lived in Europe at the time. I built such things, and I measured them. Funnily enough, I got a beta of like 50 to 100. This was in an older technology, and the doping of the base was very low, so the recombination of this base, recombination rate was very low. So the beta was pretty okay, but the alpha was like 0.1 because 90% of the current disappeared in the substrate. Well, it was interesting. Got me my degree, right? So good. Okay. Well, so there are obviously the active devices, NMOS, PMOS. These are the workhorses. If we can do anything with an NMOS, or if it has to be a PMOS device, that's what you're going to use, because they're going to be the cheapest, best, and so on. That's where the billions of dollars of development go into, right? Sometimes, if we build a reference, for example, we will try to use the parasitic PNP transistor. The diodes, rarely useful. Okay? Well, rarely useful. Let me take that back. I mean, these diodes, of course, provide isolation of all of our transistors. If we didn't have them, we could put just one transistor on our IC. That wouldn't be very attractive, right? So, but beyond that, I mean, so if we take that for granted, right? Beyond that, diodes are not that useful as circuit elements. Okay, so if you were a digital designer, you pretty much would say, great, what else, right? That's all I need. If you're an analog designer, you will say, well, gee, I mean, sometimes at least, like again, for example, in a reference, a resistor kind of handy, right? I kind of need it, and we'll see capacitors. We have just an unending appetite in our circuits. We'll have just a non-ending appetite of capacitors. We know in compensation circuits and so on. We're going to use them for everything, for all processing and for feedback networks. We're always going to use capacitors. So we somehow need those two. And inductors, well, sort of for mixed signal design, hundreds of megahertz bandwidth or so, inductors are not really there. Right? When we go up to gigahertz RF amplifiers on 242, then of course we're going to use inductors. But here, the inductors we have available, so we're not going to talk about that. They're not going to be useful for us. But resistors and capacitors, they are not only useful, but we actually need them every once in a while, and so let's talk a little bit about them. So again, it actually turns out that the in number of transistors fabricated, actually that would be something interesting to figure out once if you have a little bit of time. What is the fraction of transistors, of all the transistors fabricated, what is the fraction that is used in digital circuit, and what is the fraction that is used in analog circuit? I would guess that 1 ppm is a gross overstatement for analog transistors, right? They're just that's why we give them names, Fred and Alex and Sonia and so on, right? But you can look at that also, of course, at a slightly more down to earth and dollars kind of thing, and there you will see that total revenues of the IC market. What is the fraction that is spent on analog circuit? What's the fraction that's spent on digital circuit? Well, I have to admit that the analog circuit margin has been eroding a little bit, but we are still at close to 20% or so. Especially if you could, if you have a DSP that uses 1 million transistors, but in the corner there is this A to D converter that actually makes it a product. Well, the analog guy ought to get some credit for it. So in terms of revenue, analog circuit designers don't do badly. So, okay, but nevertheless, if you go to standard CMOS, then that's for the digital designer and the analog guy. Who are you? We don't even understand your problem. So resistors are, of course, bad for digital circuit. They slow things down, and consequently, the process engineers at TSMC or name it, they work very hard and over time and get their bonus for making resistors be essentially zero. And so now if you look at that, aluminum, of course, has a small sheet resistance, 60 milliohm per square. This per square business, everybody knows what it means. Okay. Polysilicon's a little bit more, 5 ohms per square. Diffusion also like 5 ohms per square. These numbers, incidentally, of course, they're always technology dependent, right? So I give numbers that are about typical, and when you start designing, you got to get the process manual, and you have to look at what these numbers actually are for the process that you are using. But so here we have numbers that also give some meaning. Annual tends to be a much higher resistivity, and there are actually 2 reasons for that. We'll see in just a moment. Yes. What is the? What are they? 10 to the. Yeah, 17, 16, 17, 18. I mean, it keeps going up. Yeah. Yeah, why is this difference so big? Let's look at the next slide. But before that, let's just look at how big the problem really is. Suppose we need a 100K resistor, right? We don't want to make it out of a well. I mean, it's kind of a bizarre, right? So we use polysilicon. They also tend to be a little bit better. We'll get to that. So we make this polysilicon thread 1 micron wide, and in order to get 100K, and we get 5 ohms per square, so per 1 micron of length, we get 5 ohms. Well, we need 20,000 microns or 20 millimeters. Well, of course, we're going to lay it out as a serpentine, right, so that we somehow fit it into this chip that is only 4 millimeters on the side. But, you kind of have an option, right? You either can put one 100K resistor on your chip, or you can put an entire Pentium processor on that same chip. The choice is yours. Now, how are you going to make more money? Well, I mean, the resistor kind of tough spot. So I haven't forgotten your question. So the good thing is that analog circuit designers, they're pretty flush with money, right? 20% of the markets are. So we got dollars. So the foundry guys, they say, well, give us some of them. And so they make available process option. That has become a big business. Now, if you go to TSMC and or some foundry, right, UMC with the same deal also, you get to choose from maybe 3 or 5 different technologies that they offer, and then per technology they may offer you 50 different options: high voltage, low voltage, big threshold, whatnot. I just mentioned here a few, right? So you get the base technology, the baseline process, and then you just add, sort of like a menu, a la carte. You add stuff, and stuff that the analog designers like to add is a capacitor option. There we add the second poly. Of course, you get to pay a little bit extra now for doing that, but if our chip now performs better, well, maybe we make more money on the chip, right? Sometimes we add low VT devices, and my students, they're designing an A to D converter in a 0.13 micron technology, and they tell me that they have alone transistors, they have about 24 different ones to choose from. Okay, so high voltage devices, well, in a 0.35 micron technology, that's usually not that big a deal, but in a 0.12 or something like that micron device, very often you have a high voltage option. Even the digital guys often want it because then they want to interface to a legacy IC that operates off 3.3 volts, so you can get high. E-squared PROM is a very popular option if you want to trim something or so. Well, why not store the trim information in an E-squared PROM, right? And of course, if you want to configure a digital IC, then you also want E-square. So maybe the digital designer and you, the analog guy, can sort of split the cost for that option. And then, and that's the one we are getting here, is the silicide stop or silicide blocking option. What is that? Well, so here is our transistor. And the way it's made is that we use the polysilicon as a mask, and then we use an ion implanter, and it shoots ion into this thing, and it makes the source or the drain. It looks like this, right? Now, the source or the drain, the doping has gone up. Now it's 10 to the 20th, 10 to the 21st, whatever, right? It's almost a metal. So it's highly doped. But nevertheless, the sheet resistance here is fairly high. And you know, I mean, if you use the thick metal, white bus, and so on, then you get into the source or into the drain region of your transistor, and you actually add more resistance there than in your entire metal interconnect. Well, the digital folks, they don't like this because it prevents them from making Pentiums that go at 3 gigahertz. So what they do is or the processing guy does it for them, again, for that's standard actually, you don't even have to pay extra. Puts a silicide into this thing. So I've forgotten exactly how this is done, but a metal is put on top of the junction, usually titanium or tungsten or something like that. And then the thing's heated up, and it makes a so-called silicide. It's neither that metal, nor is it just the silicon. It's some kind of a combination of the two things, with the net effect that it has higher sheet resistance than the metal, but lower sheet resistance than the silicon. Okay, and I guess the reason they do it like that is that it's kind of tough to have a junction in a transistor made out of a metal, right? It's no longer a transistor, so the silicide is kind of attractive there because it leaves you with the transistor. Okay, so it's really the silicide that is the reason why we get such low 5 ohm per square sheet resistance. There would be hundreds of ohms if we didn't have that. That explains also why the well has so much higher sheet resistance. Well, in the well we don't have silicide. Simple as that, right? So here we get 1 k ohm per square. And here we have the 5 in the silicide option, and here we have maybe 100. Or this difference, of course, is simply because of different doping concentration. Okay, so now we've paid our extra money. We got the silicide block option. Now we have a plethora of new devices. New layers that we can abuse as resistors. Just don't tell the digital guy. Cause him sleepless nights, right? So here is the sheet resistance in ohms per square. And so N plus poly now suddenly is no longer 5, but it's 100. P plus poly is actually 180 again. Different doping and different mobility and so on. N plus diffusion is 50. P plus diffusion is 100. And the N val is unchanged at 1K per square. Right? So if we want to make a resistor, then we use this non-silicided stuff. So because here we have 100 instead of 5 ohms per square. If you go to our example from the previous slide here, this would drop by a ratio of 100 over 5 by 20. So instead of needing 20,000 micron, we need now 1,000 micron. Still not small, but you know it's no longer entirely sort of ridiculous. Okay. So the minute we've solved that problem, of course, analog circuit design is exactly right. We always worry. We are the worries, right? But then we get stuff working. That's the key, right? So the minute we've got this problem fixed, we have another one. We have the temperature coefficient. In other words, we want to make a 10K or 100K or name it resistor. We wanted that to be that valuable, but then it changes its value because it gets warm, it gets cold. It also changes its value. Heck, I mean, can you imagine? I mean, it's really unbelievable. You take a resistor. I mean, what is it for? I mean, to run current across, right? Current through, and so you put the voltage across. The value of this resistor is not only a function of temperature, but it's also a function of the voltage across the resistor. Isn't that ugly, huh? Well, it is. I will see just in a moment why that could be, but there again, right, I'm not too interested in devices. I want to get the best ones, then beyond that, I use them and I'm clever and sort of building a good circuit despite their shortcomings. So we're not going to focus as wide as this, but how do we survive this, right? So first we're going to look at the temperature coefficient. So that's just saying, well, the value of the resistor is a function of temperature, and what are we going to do with that? So first of all, the way that the temperature coefficient is for a resistor is described as a TC, that is, for example, minus 8, can be positive or negative, 800 ppm per degree C. In other words, a resistor changes by 800 ppm, or just a little bit less than 0.1% for every degree. So in other words, if we have a 1K resistor, we change the temperature by 10 degrees, then the value of that resistor would be changing by 0.8%. Change it by 100 degrees Celsius, we get an 8% change over the resistance value, or in other words, 80 ohms, right, on a 1K resistor. So how do we then describe our resistor? R is a function of temperature is equal to some bias value at a certain temperature, T equals 300 degrees Kelvin, for example. You have to know what that is, right? Whoever measured the resistors so as to tell you at what temperature he took the measurement, right? And so then it's 1 plus Tc times T minus T0. So that's the value of our resistor. Or this is basically delta T. The difference of the temperature of the resistor from the temperature at which the value of the resistor was specified. Okay? Okay, let's look at an example. Okay, I'm not very imaginative, so I stick with my 100 k ohm resistor, but now I want something else. I want a TC that is equal to 0. In other words, I want a resistor that is independent of temperature, at least to first order, right? So, use our table. Here is the TC of our resistor. Which one are you going to use? We want 0. What are you going to use? We're stuck. See, that's again sort of the analog circuit designer thinking, right? I hope I'm going to get to that a few times, right? So we look at this and we say, gee, I mean, temperature coefficient, what a drag. I mean, they all ought to be 0, or if not 0, at least they all ought to be small, right? But now we want to make one with 0 TC, right? Then we say, well, gee, I mean, looking at that, some of them are positive and some of them are negative. Heck, I mean, if we make a resistor that is made out of two different resistors, one of them increases with temperature, the other one decreases with temperature, we ought to be able to net get 0, right? TC. Of course, that's only to first order, right? At one temperature, it's going to be like that. If the further you go away from that temperature, it's not going to be. It's better than nothing. Sometimes very helpful. And in fact, the device engineers, they are not so unappreciative of analog circuits, folks. They actually do it sometimes on purpose, at least the good ones. They make it on purpose. I don't know. I even don't know how, right? But thanks for them. They somehow turn a button on their big machine, and it makes it that one is negative, the other one's positive. And they do it reliably, all the time, every day, million wafers per year. Huh? A few million wafers per year. Okay, so we're going to take a positive and a negative one, and then we just ratio the two resistors just right, so that overall we get 0 TC. And that's shown here. Now the rest is math, right? Once we know that, it's math. Basically what I do is I write the value of my resistor now as a sum. I use N plus and P plus poly resistors because they have positive and negative TC respectively, right? So I use a certain amount default resistance for the N plus poly and probably different amount that I'll have to figure out of the P plus poly. And here are my temperature coefficient. Then I rewrite this a little bit. This is the constant part, doesn't depend on temperature, and that constant part better be equal sums to R, right? And then this part here is what changes with temperature. Well, I mean, ideally, of course, would be I just make delta T equal to 0, but not everybody is living in an air-conditioned room, right? And some people actually want to go outside sometimes, so I can't do that. So instead, I make my TC. I make this other thing to 0. So now I have two equations and two unknowns, Rn and Rp, and I can solve for those, and I find that I need 200 squares for my N-channel resistor and 400 some odd squares for my P-channel resistor. That's it. Then I have a 0 TC. Clever, huh? So, what is a bad thing sometimes for an analog designer is always an opportunity to do something clever. Problem's gone, right? Okay, so now we talked about the voltage coefficient. So again, I mean, there are probably some people in here who actually know devices. And you'll know this stuff a lot better than me. So I keep it purposely at sort of a little bit the high level, right? And then you still can correct me, of course. So let's assume that we had a diffusion resistor. What is a diffusion resistor? Well, it's an N plus or P plus diffusion. that again has, because of finite doping, it's not a metal, right, has some resistance, and that's sometimes helpful. Now, very often we actually put our resistor into a shield rather than putting it directly into the substrate. Anybody's got an idea why? Why bother with this end wall here? Why not stick it right into the substrate? Well, the substrate is shared by everybody. Every circuit goes into the same substrate. And every circuit invariably is going to inject a little bit of current, electrons, carriers, into the substrate, and they produce voltage differences. And these carriers also, they ultimately get sucked up by something again, right? Heck, if these carriers end up in our signal, ooh, not good, right? So we want to shield our circuits and our signals, more specifically, from this substrate, right? Of course, we're going to put in all sorts of contacts in the substrate, and we put the digital stuff. You go way over there, and the analog stuff is over there, right, and so on. But nevertheless, we take our precautions. We isolate as much as we can, right? Because we don't want to get 60 dB of isolation. We want to get 100 dB of isolation. That's very hard. You do everything that's in the book, and then a few of your own ideas. So we put this diffusion resistor in a well. So the substrate wiggles. Then the well is tied now to a clean, let's say, analog ground or whatnot, right? And we'll have to talk about it, what that signal could be. Something that doesn't wiggle as much, right? And consequently, this thing here is going to wiggle a lot less than the substrate. If something's wiggling, this is going to wiggle less, right, if you did it right. So we're going to get less signal coupling. Okay, so that was a detour. There's so much interesting, little subtle, nifty little stuff in analog circuits, right, to talk about. That makes the difference. So now we get back to our junction transistor. Well, if we want a resistor, we wanted to make a resistor. So this is, in our case, this is P and this is N. Well, right. So if we use it as a resistor, so we put here, let's say V1, and then here we have VB. Then basically the voltage in between here is going to be V1 minus VB, right? Well, that modulates this junction. It modulates the depletion region, right? Okay. If we increase or decrease that voltage, the width of the depletion region increases, decreases. Actually, can you say J-effect? That's exactly how a junction field effect transistor works. Like, for example, Graham-Meyer described. They're not that commonly used today anymore. Really, boutique stuff. If you have one, then you probably can make a lot of money because they're sort of dying away, and in some cases we really need them. But anyways, this junction which changes. Well, that means that the amount of material that's still available to carry the current from our resistor between here and here is changing too. Heck, I mean, if I make my resistor wider or narrower, of course the value is going to change. I mean, sure. Okay, so this got to have a voltage coefficient, and it's directly linked to this junction business here. Now, you may say, well, then I just use a poly resistor. Well, aside from poly still having a somewhat lower sheet resistance, so that reason may not want to do that. Poly also suffers from this effect, because poly also is just doped, and you can, of course, it doesn't have a junction there, but if you have a strong field across poly, you get all the carriers to one side, and at some point, they're filling all the, what is it, the acceptors, or don't know, whatever, right? They fill up all the states, and then if you want to put more carriers there, well, sorry, this parking lot's full, right? And so you get the, right? So if you have poly over substrate or so, as you put more and more carriers on this, the first they go all here, then the next layer of carrier goes here, so on. All right, so we get a voltage coefficient. So if we get a voltage coefficient, well, we can hire someone or do it go ourselves to the lab and we just figure out what the voltage coefficient is for all of these devices. Then we have again a similar equation as for the temperature. Now it's R of Vc not R of V, I guess. R of V. How do I call this V? Yeah, V. R of V is equal to R0 times 1 plus Vc times V. Right. And this Vc is in ohms per volt. Oh no, well actually no, it's in ppm per volt because I multiply with the resistor later. Okay. Of course, the reason actually why I do that, why I specify it in ppm per volt rather than in ohms per volt, is that then I get one number independent of the value of the resistor. Otherwise, I would have to give you an entire phone book. Right? For every resistor value would be a different one. Okay, so that's the voltage coefficient. So now in practice, of course, if you can zoom in here, please. Just this equation. Okay, thanks. Don't change the zoom. I move my slide, but you don't worry about that. So what I'm going to have is I have two terminals with my resistor that is at a certain temperature T, and then I also have the volt terminal that is yet another voltage, right? And of course, all of these are going to affect, right? If I introduce a huge gradient between V1 and V2, it's going to make the diffusion big or small in one terminal, less than the other. So it's going to affect the value of the resistor. If I just change VB, it also modulates this. So we're going to have dependence on this, and then the whole thing on temperature. Now I can lump all of these together, and I did that in an equation here. Here's the TC business that we've talked before. Here is this VC business. That's really the voltage between the potential in the resistor. Well, that's actually the voltage across the resistor between V1 and V2. And then there is also the third term here. That's the voltage difference between the value of the voltage in the resistor and the value in the well, the voltage value in the well. And now, of course, that's going to change. That's going to vary across the length of the resistor. So one way to deal with that is to say, well, gee, I mean, it's a small effect. We linearize it. We use first order Taylor series expansion, and then we just use then we can use just the value of the voltage here in the middle, right? So that's why I specify here V1 plus V2 over 2 as the voltage in the resistor.